Okay, yeah, that's weird. Oh, man. Okay, I'm going to start out by calling your name. You can come up and pick up your test. I don't think these are in any particular order, but I'll shuffle them up a little bit. Okay, Jorge. Oh, you know what? I need to explain something before I hand these back. All right, so when I hand these back to you, on the first page of the test, in the top right-hand corner, it'll say like minus 21, and it'll say like plus 3. And then on the second page, on the bottom right-hand corner, you'll have something like this. I'm just making these numbers up. 74. Then you'll have a line. It'll say like, let's say 71. And then you'll have something like 101, 83, 64. I'm just making these numbers up. Do y'all see that? Okay, so let me explain what everything is. The test was 10 questions plus a bonus. Number 8 turned out to be much more challenging than I guess I had intended it to be. But so what I did is I threw 8 out and only counted it as a bonus, which means that there were only 9 problems on the test. Each problem was worth 10 points, so there was a total of 90 points possible. So for this particular student that I'm making up, they had 21 points taken off out of 90, right? Which I'm trying to remember how I did the plus 3. I think I did the plus 3 at that point. So that really would have been the same as taking off, what, 18? So if you do 90, you take away 18, and you divide by 90, then that's the grade that the student got on the test, all right? Make sense? So this would be what, like 72 out of 90, right? Do that on your calculator, and that's what your decimal grade is. So what these numbers represent, and please pay attention because I don't want to go through this 100 times. The boxed one is your average in the class right now, is where you stand in the class. This one down here is what you got on this test. All right? Make sense? So average in class, average on this test. These 3 numbers represent what you need to average the rest of the way to get an A in the class, a B in the class, or a C in the class. So for this particular student, to get an A, they would need to average 101 the rest of the way. That means it'd be tough, but it could maybe happen with some bonuses, right? For a B, they need an 83. That means on the next test, maybe they could get an 80, but then on the final, they'd need something higher than 83, right? So averaging out the rest of the way, they need this. And then to pass, to get a C, they need a 64 the rest of the way. That gives you some idea of where you stand, right? Okay, so let me hand these back. I'm going to pause my video so I don't call all your names out on video. All right, so as far as the exam, the grades, we had 25 students take the test. I think we started with 28. I could be wrong. We had 25 take the test. We had, these are in order of lowest to highest, so low being 27, high being 102. We had 6 A's, 6 B's, 6 C's, 3 D's, 4 F's. This is actually one of the best distributions I've ever had. It's normally in a math class, your distribution is like an inverted bell curve. It's usually like that. You usually have like the people who get it and the people who don't get it, and not a whole lot in between. So this is actually, I'm very pleased with this distribution because it looks like a majority of the class is still in the game here, right? And even these 3 D's were really close. Like 2 of them were really close to C's. So that's good. Yes. Yes. It's out of 90. No, go ahead. I have probably not. Probably not. Yeah. I'll do that all at the end. I just went off a raw grade of what you had right now. The average on the test was a 75.56, so about a 76. And then the standard deviation, that I still wasn't very pleased with, but that's pretty normal. 19-point standard deviation means that most people were within 18 points of the average. But that's a pretty big window, isn't it? I mean, like 75 plus 18, 75 minus 18, that's a huge window. The smaller standard deviation is better. That means more people are, everyone's kind of closer together with their grades. So we had a real big spread of grades. But that's, I think, to be expected with so many A, B's, and C's. It's spread out. What else? Data-wise, I don't know. I guess the only thing I can say is, you know, to me, this average of a 75, you know, is a mid-C, right? It's a mid-C. So when you look at, you know, what the letter grade system means in college, C means average. If you're a C student, you're an average student. Now, if you're trying to transfer into a program, they want high GPAs, right? They want you to be above average, you know, when you look at your GPA, which would make sense. I guess they can't take everyone into a program, right? So that's what they do. They look at your GPA. But in terms of this class, for the class average on a test to be average is okay with me. It means average is average. Now, if the class average was like a 62, then that means that the average grade was below average, which means the test was probably maybe too difficult. I don't know. You know, there's different ways I can look at it. But whenever my average for a test lands at what a C is, I'm okay with that. And the fact that I did have A's, right, have 6 A's means that, you know, that's okay. If I had no A's, that would worry me. You know, what this means, of course, B is above average, right, above average. And then C is exceptional, right? I mean, A is exceptional. Did I spell that right? I'm missing something there. C, right, after the X? Yeah, exceptional. Right, so that, I mean, I'm just trying to get us to be real about what the grading system is, and then, you know, below average and then not passing, whatever. I've really had to think a lot about this because my niece she lives in Europe right now, and she wants to go to Texas A&M, and she went and visited with them. She wants to get in their biology program, and because she's taken some credits in Europe, she can't come in as a new student, so she has to transfer in, which means that she has to take some courses here. And one of the classes she's going to have to take is Cal 1, I think. Anyone doing A&M biology by chance? No? And so I was talking to her about it, and it's all about your GPA. You got to keep your GPA high. So I realized that for some people, like a C average in this class is not going to help as far as getting into a program. It won't help, but that's why your other classes, you want to keep your GPA high. But calculus is calculus. I can't make it something it's not. It is what it is. So, but I am aware that GPAs are important. It's not that I'm not trying to force everyone to be, at a C level, or I'm not trying to force the average to C. If I had 20 A's on this test, I'd be fine with that. Okay, now questions over the test. You wanted to know about the bonus. I don't believe that I have anyone that still needs to take the test, so I can share this with you. Let's see, exams. Oh man, I don't have the solutions. Oh wait, I have them right here. Well, this is a related rate problem, so why don't we work it, because that's what we're going to do today, is more related rates. So this will be a good segue into what today is about. So let me get to today's notes, and we'll start with that question. But before I get into it, were there any comments or concerns or anything about the test that you want to say openly? I mean, if you have something on the test that you're like, you have a specific question about your test, then let's save that. But anything general? Any general questions? I invite you to come by, and if you want, we can go through your test. I would encourage you to go try and figure out, what you did wrong before, because I usually don't show a lot of the details to what you got wrong, to try and encourage you to go figure out what you did wrong. Each problem was worth 10 points. So if it was -2, it was minor. If it was -8, it was big. All right? Yes? Number 8 on the test? Oh, yeah. Well, you're going to get real mad when I show you what 8 was. What I'll do is I'll put a problem like this on test, and I won't make it a bonus question, but it'll be a very challenging question just to see how people handle it. The problem was, let me get this written down. I believe it was, here's the graph, and then you were supposed to figure out where it was parallel to this line, right? Was that the way I wrote the line? No. I just put y minus x equals 5. So what I want to know is, when is the derivative of this equal to the slope of the line right here? So first let's find the slope of this line, which would be moving everything over, getting the y by itself would be this. The slope of this line is 1. And so now I need to figure out the derivative here. So the derivative is just, this is not implicit differentiation, it's just a regular old derivative. So I do have to apply the chain rule, because I have a polynomial sitting inside of a square root. So I first say, what's the square root? What's the derivative of the square root of something? It should be 1 over 2 times the square root of that something. Then times, now I'd go and take derivative of what's inside here. The derivative of x squared is 2x. And then the derivative of negative 2x is negative 2, or minus 2. So that's what you would have right there. And so let me clean it up. I'll put 2x minus 2 over 2 root x squared minus 2x. And I'm going to do a little bit more cleaning up. I saw some people did this. They realized that there was a 2 here and they canceled, but this 2 has to also get canceled out. So you can look at it like this. Factor 2 out of the top. And then cancel those. And so your derivative is x minus 1 over square root x squared minus 2x. If you got that or something close to that, you probably got plus something. If you just got the derivative, right? I did give you some credit for that. Is it okay with the lighting like this? Yeah, okay. So that gives you some credit. Now, you need to know when that's equal to 1, right? That's the whole idea. When is that equal 1? So I take this x minus 1 over the square root of x squared minus 2x. I set it equal to 1. And now I try and solve this equation. So what I would do is I would multiply both sides by this denominator to get it off the left side and get it to not be a fraction. So multiply by that root on this side, multiply by that root on this side. They cancel out here. I get x minus 1. Over here I have the root. This is what we call a radical equation, a square root equation. And to solve a square root equation, the first step is to isolate the square root and then square both sides of the equation. So I already have an isolated root. I need to square both sides. So I come in here and I square the left and I square the right. Now when you square the left, you have to FOIL it. You can't just square each term, right? You have to FOIL it out. And when you do that, you get x squared minus 2x minus 1, plus 1, sorry. Is that all right? Then on the other side, when you square the square root, it goes away. You get this. Any questions with that? And now this is a quadratic equation, so we move everything to one side and try and solve it. So I'm going to subtract x squared and add 2x to both sides. And over here, on the right side, what do I have? 0. On the left side, do you see what happens? And you get just 1. So you get 1 equals 0. 1 doesn't equal 0. Which means what? There's no solution. That means that it's the tangent line to this curve is never parallel to that line. So if you got this even, and you came out to something here at the end that didn't make sense, I gave you more credit. Who got, like, someone got plus 8. Who got plus 8, right? You put something like never or something like that. It doesn't happen. Anyone get like plus 5 or 4? Plus 5. So you probably got all the way down to something that didn't make sense, but didn't draw that final conclusion of, well, then it doesn't happen. And that's, again, I understand if you want to throw shit at me, that's okay. But the thing is, it's really understanding the idea that you can work out a problem and you can get to a result, and then really you have to step back and think, well, what is that telling me then? It's telling me it doesn't happen. Now, what I'll do, just to reinforce this idea, is let me graph it. All right, so we had square root of x squared minus 2x, right? That was one of them. And then the other one was x plus 5? Y equals x plus 5? All right, now it's difficult to tell from this. There it is. Okay, you see this tangent line? Can you all see my tangent line right here? At this point, that's the tangent line? Yay or nay? Yes? Okay, notice this. I'm trying to see when is it parallel to that blue line. And you can kind of tell from here it never happens, right? I mean, obviously on this side, the slopes are, one of them's negative, the other one's positive. If I go to the other side over here, see this? It looks, those don't look parallel. It looks like maybe it happens, but it actually never does. See, the further I go out, it starts to go like that, but it never actually gets fully parallel with the blue one. Sorry, that's why it was bonus. But I also remember at the beginning of the test, I gave you very specific instructions. I said, if you get hung up on a problem, at least get the derivative and then move on to something else. This was exactly why I told you that. At least get the derivative, and if the rest of it's causing problems, do not get bogged down. That's actually something that is a skill that you should work on for testing in math, at least, because what I see is students, even in my Cal 2, Cal 3 class, they're very bright students, but they'll let one problem eat up 45 minutes of the test. And then after that, they can't do the rest. So you don't ever want that to happen. It's better just do the best you can with what you can do, and then just cut your losses and go to something else than to try and get too bogged down on it. Make sense? Okay. All right, who else came in so I can get these exams back? Sean, Mark, Brooke? Sean. And I have all these additional little numbers that I explained to everyone in the beginning of class. We can talk if you want afterward. Trick question, huh? Kind of. All right, now the next question, and what, yes. Oh, I'm sorry. Oh, there were more here. You are Paul? Okay. Here you go. All right, so the other question was the bonus, right? And since everyone has their test, just flip to the bonus. Now look, when I give you a bonus problem, usually the bonus is all or nothing. Because it's a bonus, it's got to be dead on or nothing. I usually don't give like partial bonus. Now on number 8 I did, because number 8 I think warranted that. But with this bonus, most people it was either all or nothing. And I think only one person got it, I believe. So everyone has a problem, right? So I don't have to write it down. A sphere is growing such that its radius is increasing at a constant rate of 10 centimeters per minute. A sphere. So we've got this sphere. It's growing, right? Its radius is always changing at the same rate. It says find the rate at which the surface area is increasing when its radius is 5. So I like to always start these out with 2 pictures, right? I have a picture of the general situation when things are changing, and then I have another picture of exactly the moment in time we're talking about. It doesn't matter which one you put on the left or right. So in general, I have a sphere. It has some radius to it. That radius is changing, right? It's as time goes on, that radius is growing. For the instant in time that I'm talking about, that radius is what? 5. And if you want, you can put centimeters, you don't have to. While I'm drawing my pictures, I'm also trying to come up with the things that I'm given and the things that I want to know. So I am given, the very first thing that it says here, after it says it's a sphere is growing, is that the radius is increasing at a rate, and I said rate always stood for what? The rate is a derivative, right? So it's like a d something dt. So I'm giving you the rate of the radius, the rate of change of the radius. So what's given is the change, the dr dt, right? The change in radius with respect to time is what? 10 centimeters a minute. Again, we don't need the units, but I'll put them in here anyway. What is it that you want? Find the rate. So I want a derivative, right? Find the rate at which the what is surface area. So I'm going to say I want the change in area with respect to time. When do I want that? At exactly the moment what? When the radius is 5 centimeters. I'm given the rate at which the radius is changing with respect to time. I want the rate at which the area is changing with respect to time. I want it exactly at the moment when the radius is 5 centimeters. I think that's probably good as far as our pictures, as far as what we're given, what we want. Now I need to find an equation, right? An equation, any equation that exists that relates your radius to your area, right? Look how great that highlighter works, right? That projector works pretty good. Radius and area, right? So now you have to break out your formulas, which you were allowed to have on the test, right? And there is a formula on the, I think it's the very first page of the formula sheets. It gives you the area of a sphere, which is what? The area of a sphere is 4 pi r squared. You would have had to have referenced that or known it. I believe this, does the formula sheet say SA? SA? Surface area, same thing. What do you do after you have the equation? Take the derivative, right? Do I plug in 5 for radius now? No, you do not plug in. You do not replace any variable that's changing in the problem until after you do the derivative. So, like if I fix radius at 5 right now, then the entire right side is just a constant. So if I take the derivative, it'll be 0. So that's why you can't do it. So I leave it alone, take the derivative with respect to time, right? So what is the derivative of A with respect to time? dA dt equals 4 pi is a constant times, so I'm just bringing this constant straight down. What's the derivative of r squared? Chain rule, right? Power rule first, well, chain and power. Power rule 2 comes down, times r, but then, very important, now you go inside and take derivative of r. What's the derivative of r with respect to t? dr dt, which will be 10 in a minute, yeah. Any questions on that? You sure? Okay, now it's just a matter of plugging everything in. I wanted to know dA dt, so there it is. 4 pi 2 r. Now can I fix r? Yes, because I've taken the derivative. R is going to be replaced with 5, and then dr dt is given to me in the problem to be 10. So I'm going to replace that with 5 and that with 10. 400 pi, I believe. dA dt is 4 pi times 2 times 5 times 10, which is, it's 400 pi. Now we need the units. So A is area, right? A is area. Areas are measured in squared dimensions, right? Squared dimensions. So what is our unit here? Centimeters, right? Centimeters squared would be our area per, because it's divided by our measurement of time. Our time here is minutes. So at exactly the moment that the radius is 5 centimeters, the area of that sphere is increasing at a rate of 400 pi square centimeters per minute at that instant. I know some people did this problem, but they used the volume formula instead of the area. And I think there were maybe like 2 or 3 that used the right formula but didn't quite get the right answer. And I know someone did get it, yes. No, I'll look at it. Really? Let me see it now. Anyone who got that right, 400 pi, I either overlooked it or you just wrote it all out. Good job. No, I believe. Really? Oh, wow. Okay. Thank you. You know what it is? I know exactly what it is. Y'all finished early, didn't you? You were one of the first group done? I think that's what it was, because I graded these in class. And then I went home and graded the rest. And when I graded the rest, I graded their bonuses. I never got to your bonuses. So, sorry. I will correct these. Okay. Yeah, if you got that right, it's +8. If it's all right. All right. We ready? More related rate problems? So if you are following along with videos, there's a bunch of examples that I plan on doing in class. They're all related, but they're all a little different, all right? Every one of them involves its own sort of attack, right? They all have their own sort of geometry that's involved, but they all have something in common in the sense that you'll always try and draw pictures. You'll always have to come up with an equation. You'll always have to differentiate it, and then you always have to plug stuff in, all right? But there's no limit as to what formula we have to grab. Could be surface area, could be, like in this one, some stuff with right triangles, could be trig functions. All right, a plane is flying horizontally, right, at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. At the moment the plane is 6 miles from the radar station, how fast is the distance between them changing? So I had this little animation here. It's my plane flying overhead. The radar station is right here. I've centered it right here at the origin. Notice that as the plane flies over, the height is always 2, and we're not looking at the curvature of the Earth, and we're just assuming horizontal is flat, the ground is perfectly flat, right? You want to do it for real, you have to take all that into account, but that's not where we start. We start with just basic idea here. So straight, right? And I want to know, let's see, at the moment the plane is 6 miles from the radar station. So what distance am I talking about 6 miles from the radar station? It's from the dot to where? 6 miles to the radar station. Where's the radar station? On the ground. So I'm talking about the hypotenuse of this triangle, right? I'm not talking about 6 miles being its shadow on the ground to the radar station. It's the actual hypotenuse. That's one of the mistakes that students will make. They'll say, oh, 6 miles from the radar station, that means 6 miles on the ground. No, it's this one. Make sense? That's the first thing. So I want to know at exactly the moment that we're 6 miles from the radar station, which is exactly here. And now it could be on this side or on that side. I didn't tell you which side, right? If we're here, at that instant, I want to know how fast this distance is changing. Agreed? In this case, it's getting smaller, isn't it? But on the other side, over here, if I were to say there, then the distance between them is increasing. Right? We all right with that? All right. So we have to start with pictures and try and figure something out. So here we go. Radar station on the ground. Now, if your radar station isn't as good as my radar station, don't worry about it. Just draw a dot on the ground, okay? I understand I'm kind of showing off here with my artistic ability, all right? Then I have a plane. Now, I'm going to humiliate you now with my drawing abilities. Yeah, check that out, okay? Look at that. Cockpit, window. Yeah, there's a wing out the other side too. All right, that's bullshit. We don't need any of that, right? We need to look at it as points. I think that's the better way to approach it, right? We got points. And what's happening is that there is a distance between these 2 points that's changing. And since that is changing throughout the problem, right, as it's flying over, remember, this is our general picture. In the general picture, you cannot freeze things in time, okay? We will do that over here at the instant in time. So if that's changing, we need to assign it a variable. So we could call it anything we want. What would you like to call it? X? You like X? Okay. I don't, but here's why. Here's why. I would advise you to reserve X for things that are running along the X-axis and reserve Y for things that are running straight up and down. It's not wrong to call that X. That's okay. But I would call it something else, just so you, H for hypotenuse, R for like a radius almost. That's fine. Let's go H. Here's another variable I would avoid. D, little d. Because when you're doing the derivative, you'd be going d dt, wouldn't you? d dt. It just kind of looks odd. You can still use little d. I just always avoid little d. You can use capital D. That's okay. So that's H. That's changing, right? And I'm going to write down here what I'm given, what I want. Let me see here. So we're trying to put all these ideas together at one time. I'm given what? Speed of the plane, right? I'm given the speed of the plane is 600 miles per hour, right? How can I represent that in this picture? Okay, but where is it? What is it on this picture? It's the dot. So this is where the right triangle comes into play. I can draw a right triangle however I want. I'm going to draw it this way instead of the way I have it on my little illustration. Do we agree this is a right triangle? Yes? Straight up, straight over. Imagine that the plane is moving at 600 miles per hour, right? Then would you agree that that side, that leg of that triangle up on top that's horizontal, is actually shrinking? At what rate is it shrinking? 600 miles per hour. So if I call that leg up there X, because it's actually parallel to the X-axis, right? That I could actually say that the change in X is 600 miles per hour. Do y'all see that? Yes? No? Yeah? So I'm going to write down with that picture, I know that I'm given dx dt is 600. Now you might ask yourself here, is it positive 600 or negative 600? It kind of does in this picture, it does. It depends on which way you want the plane to fly over, though. Is the plane flying from left to right or right to left? It's up to you, okay? So that's why you have to just kind of decide what you want. Remember, if I want the plane to go left to right, then this is actually shrinking, isn't it? In the picture I've drawn, it's shrinking. Unless I would have drawn the triangle on the other side and the plane's already gone past me, and then that X is growing, isn't it? And then I would want that to be positive. Do y'all follow me? But because of the way I've drawn it, I'm just going to put negative 600. And it would be miles per hour. So I'm saying if things are shrinking like that, it's negative. If they're growing, it's positive. What is it that I want? I don't see an R in my picture. dH dt. right? I want to know that. When do I want to know that? At exactly what moment in time do I want that? When the distance between the plane and the two are 6. So that's the h when that's 6 miles. Y'all follow this? All right, so as it is right now, I still haven't drawn my picture, my instant in time. Let me do that. At the instant in time, I've got this. And I have this is 6, right? I know that that's 6 at the instant in time. What did I not label on my triangle over here that I probably should? The y? Should I call it y? Does it change in the problem? It doesn't, does it? So you can label it 2, because it's 2 all the time, isn't it? That's an important aspect of this problem, is that you don't want to, things that are changing, you don't want to ever fix them in your general picture. But things that are always fixed, shoot, replace them with whatever they are. Because the last thing you want is another variable in the problem if you can avoid it. So that's 2. In this picture, it's still 2, isn't it? But if I know 2 sides of a right triangle, don't I know the third? So I will be able to get this. I'm going to put a check mark next to that one. That I will be able to get. And that will be the value of x, won't it? That'll be x up there. Do y'all want to go get that right now? Yeah, sure, okay. Let's do it. Let's call that x up here. Let's go find what it is. How do I find that? A squared plus b squared is c squared. So x squared plus 4 equals 36. So x squared equals 32. So x is equal to root 32. So I'm actually going to put that right here, root 32, because it's not changing in my instant in time. Well, in our triangle, we would have to decide if we're going to measure that as positive or negative to the left. I'll just leave it as positive. But you wouldn't look at both cases. Who said that? I don't know. Okay, yeah. One or the other. Say again? Mm-hmm. We might have to. I mean, here the x is the length of that side of the triangle, right? It's that length is root 32. It's shrinking though at negative 600 miles per hour. That's how fast it's changing. But at that instant in time, that's how long the side is. So you always have to keep. I mean, you're keeping that in mind. You could use negative, but the thing is, because of Pythagorean identity, you're going to square the negative anyway to become positive, so it wouldn't matter. But every problem you have to think through whether or not it would be positive or negative. Ooh. Yeah. Let's do more. You'll start to see how every problem's unique. All right. I think I've got a good drawing of the general picture. I've got a good drawing of what's happening at the instant. I know what I'm given. I know what I want. So let me try and come up with an equation now. Connecting x and h. In our general picture, how can you connect x and h? X squared plus y squared must be h squared. Yes? Pythagorean identity on that. Remember, I said it can be any equation that relates the two variables together. So I could put here for my equation x squared plus y squared, but what's y squared? 2 squared, so that's 4, must equal h squared. That's my equation. And now I can come in and do implicit differentiation. I'm differentiating this with respect to time. With respect to time, right? Everything's with respect to time, because that's what I'm looking for, right? So what is the derivative of x squared with respect to time? 2x times dx dt. Again, chain rule. Remember I warned you all about this when we were doing implicit differentiation. The derivative of x is 1 if you're differentiating with respect to x. The derivative of x is not 1 if you're differentiating with respect to something else. Remember I told you that story about going out to the clubs, and remember? Did I tell you all about that? Did I tell you all that story? Do y'all want to hear it? It's kind of stupid, but it kind of makes the point. Back when I was in grad school, okay, graduate school. Anyone here plan on going to grad school? Yeah? Okay. Let me pause this video. Hold on. Before I think of her. It's funny. All right, so the derivative of x with respect to t, right, is dx dt, not 1. Now, what's the derivative of 4? 0. Right? So derivative of 4 is 0. Now, the same thing. What's the derivative of h squared? 2h times dh dt. What has to happen with your equations, all right, is what you're looking for has to be there somewhere, right? I mean, we're trying to find dx dt. It better appear somewhere in your differentiated equation. If it's not there, then how are you ever going to solve for it? So like if that dx dt was not there and you thought derivative of x squared is just 2x, what are you going to do now? You see what I'm saying? You're not going to have anything to go after. So this is it. We're there. We have everything we need. I'm going to put some little check marks. Do we know what x is at the instant in time, right? We actually did some of this groundwork already. Up here we had solved for x, didn't we? So we're good with that. That's check. I know that. Do we know what dx dt is? We know that, right? Oh, did I say we were solving for dx dt? I did. I meant dh dt. It appears here. That's what we're solving for? Okay. dx dt, I know that. Yes, I'm good. Do I know what h is? At this moment in time, yes, it's 6. Do I know dh dt? No, but that's what I want, so I'm put a check. Like I've got everything I need here. Now it's just a matter of plugging things in, grinding out the answer. Don't look at dh dt like a fraction. Look at it as just like something we're solving for. All right? So let's replace everything. This is 2 times root 32 times dx dt was negative 600, and then equals 2, h was 6, and then dh dt is what I'm going to try and isolate now. So I'm going to try and solve this, get this right here on one side of the equation by itself. So I multiply all that out. What do I get? Negative 1200 root 32 equals 12 dh dt. Divide both sides by 12. So you get negative, what, 100 root 32 equals dh dt. And let's go ahead and get that as a decimal, as an approximate answer. So someone can verify with me. $565.7. Anyone get something like that? Is approximately dH dt. Oh, I forgot to put my units. Well, what's h here? H, go back to your picture. Is h an area? No, h is a distance, isn't it? And since it's a distance, and we're in miles per hour and everything in this problem, miles, right? Then that'll be miles, right? H will be miles, just miles though, because it's not an area, it's a length. So it'll be m miles per, and then time is measured in this problem it was hours, wasn't it? Because they gave you the speed of the plane was 600 miles per hour. So I'm going to put miles per hour, which we just do mph, right? So at that moment, the speed between you and the plane is changing at a rate of negative 565.7 miles per hour. Do you all remember me telling you that when you talk about like speeds of things, it's relative? You know, like if I throw a ball, I think I did it to you, didn't I? I was like, if I throw something towards you, we can look at it as moving away from me, positive direction, or negative. It just depends on your orientation, where you want to look. When I say the speed is negative, what I mean is the plane's coming over, right? Well, let me draw it this way. Come this way. The plane's coming over. The distance between us is shrinking, isn't it? So that speed at which it's shrinking is this. That's how fast it is. Negative means it's coming together. Now, if I were on the other side and the plane's going away from me, then it would have come to be positive answer, and that would have meant it's going away. So the worst that could happen in a problem like this is that you're off by a sign. I wouldn't take off for that on a test because you still are giving me what the rate of change is, which is the most important thing. The fact that it's positive or negative really just depends on how you want to look at it. Make sense? All right. Awesome. Next one. Same exact problem. It looks almost exactly the same. A plane is flying horizontally at an altitude of 2 miles and a speed of 600 miles per hour. The plane is headed directly over a ground-based radar station. Everything's exactly the same. At the moment, the plane is 6 miles from the radar station, exactly the same. How fast is the angle of the tracking radar station changing? That's different, right? It's not how fast is the distance between them changing, it's how fast is the angle. So I have in red here, you can kind of see it. You see that angle? So in the beginning, the angle is growing slowly, and then right there, it goes really fast, right? We talked about this last time. It's like you were watching something go by. It's like slow, and then real fast. Same thing. Right around in here, it's like speeding up there, and then it slows down, right? Can you all tell it's doing that or no? Do you agree that that would happen? Watching a car or train come down a train track? So we want to know at exactly that moment again, right up, right? So our angle's changing. Come on. Changing. At exactly that instant, exactly that instant right there, that angle was changing, right? At what rate was it changing? How fast was it turning at that instant in time? So let's draw a picture. Radar station. I tell that story about the going out thing. I hate telling it because it makes me sound like an arrogant ass, you know, to ask questions like that. But really, I mean, I was just being true to myself. Like, you can't. When I was in school, I just didn't have time. You know, like, you want to be able to go out? No, I can't. You want to come sleep on my bench with me? You know, in my office and do math all night? No. Okay, well, then this ain't gonna be fun. All right, so, oh, wait, I shouldn't do that. There's our plane coming over, right? There's our plane coming over. We are interested in the angle, right? So we need to somehow draw that angle in there. And so when I draw this line, I'm not drawing it because I'm interested in that distance. I'm interested in an angle. And the angle that I'm interested in is this one right here. Is that angle changing throughout the problem? So I need to label it. Theta? Yeah, we like theta, don't we? Is there anything else in this picture that we could put in here that's not changing? The height? This right here? We could call that 2 still. Look at that. I just drew a right triangle. Is there anything else that's changing in this problem that I can label? Yes? The what? That is changing. The hypotenuse is changing. I agree with that. I could label it H. Yes? But do you have any information about that H? Not really. You do know about the plane, though. 600 miles per hour. Is there any part of this triangle that represents that plane? The bottom, good. This right here, the adjacent side. Do we agree that this side right here, if I call that X, it is changing? Now that's the same X as we had up on top earlier. I'm just showing you there's a completely different way to set up that triangle and still get the same, same sort of effect. So that X is changing. As it changes, the theta changes. The 2 stays the same. 2 stays the same, right? Okay, let me draw my picture in time here. Okay, at the instant in time, I know that this is 2, right? I also know that the distance between the plane and the radar station is 6, right? Pardon? If I know 2 sides of a right triangle, can I find the third? Yes, but that won't matter really, I don't think, because we're interested in the angle, aren't we? So what will relate the opposite side to the hypotenuse of a triangle? Opposite and hypotenuse, sine, cosine, tangent, secant, cosecant, cotangent, sine, right? Sine. Who learned this thing? SOHCAHTOA. Who learned that? SOHCAHTOA? I told you I took over that pre-cal class this semester for that faculty member who passed away, and we got to this, and they were telling me that their old instructor did not like SOHCAHTOA, and I was like, I love SOHCAHTOA. Yeah, I've never heard that one. I just remember SOHCAHTOA as this very, very bright Native American Indian girl. She was a brilliant mathematician, SOHCAHTOA. So, whatever. SOHCAHTOA, right? Sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. If you haven't seen it, that's a way you can remember the 3 trig functions, and then all the others are just reciprocals. So, whoa. So SOHCAHTOA, whatever, acid or Indian, whatever you want to go with. Oh, great question. Why can't I label the general with the 6? Because if that plane moves a little bit further, that hypotenuse shrinks, and it's no longer 6. Do you agree with that on the picture? Yeah? So if it changes as the plane's actually flying, if it changes, you can't fix it. The 2 won't, because the plane's maintaining that height the whole time. The theta has to change, and then that x definitely has to change. So I will be able to get this theta, and I will do it by saying that sine of that angle must be 2 over 6. Yes? Sine of theta is 2 over 6. How do you find out what theta is then? If I tell you what sine of theta is, how do you tell me what theta is? Inverse trig functions. So what I would do is over here, I would take the arc sine or inverse sine of sine theta. So I take arc sine on the left. I take arc sine on the right. That's really 1/3. The inverse sine of sine, these kill each other off, which is the whole reason I did it. Do you all remember that from pre-cal? And then on the right side, you get on your calculator and you do arc sine of 1/3, and make sure you're in degree mode or radian, but know what it is you're getting. Are you in degree mode? 19.47 degrees. Sounds good to me, except I should write 47. Questions? I'm just doing this because I have a feeling I'm going to need to know what theta is. And I'm also just pointing out that once you fix everything in time, like, you can figure out a lot of information about that triangle. All right. Oh, I haven't even written down what I'm given, what I want. Given what I want. What am I given? dx dt is 600. Now, we can use 600 or negative, right? Well, in my picture, it is shrinking again, isn't it? So I'll use negative. What is it that I want? d theta dt. I want to know the rate at which theta is changing. So I want d theta dt. When is it exactly that I want that? When, what was 6? The hypotenuse. So I need to label it h as 6, right? So I should label that side h as 6. But hold on, before we start throwing too many variables in this, the hypotenuse being 6 is equivalent to me saying theta is 19.47, right? Do you agree? This theta came from the idea of that being 6. So even though I know here h is 6, I'm going to keep in the back of my mind that I may as well have said theta is 19.47. Is the same instant in time, isn't it? When that angle is 19.47, that hypotenuse is 6. As soon as that angle changes a little more, that 6 changes. That's a unique triangle right there. All right, can you connect our variables together, x and theta? Anything you can think of in this picture that would relate that angle to this side. That angle to this side. Cosine, right? Cosine is what? Adjacent over hypotenuse. Do you know what the hypotenuse is here? We would have to call it h, right? So I agree. We could write this. Now, don't write this, but we could. We could write cosine theta would be adjacent over the hypotenuse. Now, I need to label that up there hypotenuse, right? Y'all follow me here? Now, here's why I'm not going to use this. Look at the variables in here. What do I have? Theta is a variable, x is a variable, and h is a variable. Now, when you take the derivative and you have a theta in there, you know you're going to get a d theta dt. It's got to happen, all right? When x is in there, you know you're going to get a dx dt. That has to happen. But what else is going to happen is you're going to get a what? dh dt. And do you know anything about dh dt? No. Look at what you're given, what you want. You've got a connection between x and theta. Yes, this is, but you've thrown this extra variable in there that you don't really have any other information about. So is there possibly another connection between theta and x that won't have to rely on h? Tangent. What's tangent of theta? This over this. 2 over x, isn't it? So instead of this, because I don't want that h in there, I'm going to say tangent theta is equal to 2 over x. Opposite over adjacent, TOA, or trip on acid. There's my equation. I need to differentiate that, right? Let's see how comfortable you are with this differentiation. What's the derivative of tangent of something? Secant squared of that something, right? Now chain rule. You've taken care of the tangent, right? Go inside and take the derivative of what was in the tangent. What's the derivative of what's in there? d theta dt. Questions? Other side of the equation. Pardon? You could do quotient rule. You could also rewrite this as what? 2x to the negative 1 power, and then do the derivative. That's the way I'm going to do it. What is the derivative of 2x to the negative 1? So negative 1 comes out, hits the negative 2, so it hits the 2, becomes negative 2. X to the negative 2 times dx dt. Good. Chain rule, right? You've got to go inside and take derivative of that. All right, let's talk about things here. Do you know what theta is? Yes. We do, because we did that work already. So I should be able to figure out what secant of theta is. Do we know d theta dt? No, but that's what we want, right? So I'm happy with that. Do we know what x is at the particular moment in time? Ooh. No, we never solved for it, did we? Could we? Yes. So I'm going to have to go back and get that side over there. Right, the x was the bottom leg right here, the adjacent. I'm going to have to get it. So I'm going to put a check. I don't have it yet, but I will put a check because I will be able to get it. And then dx dt, that's given in the problem, right? That's the plane. So let's get x. I'll do it here. Yeah, that's what we solved last time, right? Yeah, so this is square root of 32 without showing the work since we did that last problem. So this is x. So let me rewrite everything. I need to do secant squared of theta is 19.47 degrees times d theta dt, which I don't know what that is, equals -2 times 1 over root 32 squared times dx dt, which was -600. What happened there? Where did that 1 over root 32 squared come from? X to the -2 really means drop x down to the bottom, right? And square it. So that is 1 over x squared, which is same as x to the -2. Any questions on where any of this came from? Now, someone's probably going to go and try and, on their calculator, where's my cursor? Go and try and figure out what secant of 19.47 is, which is fine if you want to use your calculator to do that. But come up here, just look at this triangle for a second. That's my triangle, isn't it? At the exact moment in time, that's 19.47. Yes? If I ask you what secant of 19.47 is, isn't secant the reciprocal of cosine? Isn't cosine adjacent over hypotenuse? Yes? So wouldn't secant be hypotenuse over adjacent? So this right here, I don't need to plug into my calculator if I just look at this triangle. This right here, not squared, but just the secant of 19.47 should be this side divided by this side. Y'all follow that? So I'm trying to solve this. I need to go to the next page. I'll bring everything. So this becomes, what do we say it would be? 6 over root 32. But then squared. Why is it squared? Because it was secant, right, but squared. So we do the secant first. That's the hypotenuse over adjacent. And then we square it. Then times d theta dt equals, over here, what do we have? 1200 over 32. Let me square the left side here. This is 36 over 32 d theta dt equals 1200 over 32. Y'all still there? And now what I'll do is I'll get d theta dt by multiplying both sides by the reciprocal. So when I do that, 32 over 36, 32 over 36. We get the 32s to cancel. 1200 divided by 36. What? 33.3. And that's an approximation because we used our calculator, right? Now, well, hold on. Let's talk about that. Are there any questions on that setup, though? I didn't. Someone else on their calculator said that they were in degree mode, and they did the arc sine of 1/3 on their calculator. Arc sine of 1/3, or inverse sine. It's on a key on your calculator. And then you got 19.47 also. Okay. That's because what I knew was that this theta was connected to this triangle, right? This right here. I know that sine is the opposite side divided by the hypotenuse. So I wrote sine of theta is 2/6. I wanted to know what theta was. So to get theta out of sine, I have to come in with the inverse sine on both sides, which is what I did right here. When you take the inverse sine of sine, these cancel and you're left with just the theta. When you take the inverse sine on the right side, you have to get your calculator out. Now, this is a little bit tricky. Our units. Theta is an angle measurement, isn't it? And time here was in what? Hours? Okay, so watch. We know this is per hour, right? But how do we measure angles? In degrees or in radians? So you might be thinking to yourself, well, wait a minute, it's got to be degrees because we use degrees throughout the whole problem, right? Yes? However, that's not going to be the case. This will be in radians because maybe in pre-cal they pointed this out. Radians are basically a unitless measure. When you do a problem in calculus where you get a change in angle with respect to time, your answer will always be in radians. Always, always, always. Now, if you want to convert it to degrees, you can. See, because look, this angle right here, remember where we got this right here? This does not matter if that's degrees or radians. It has no impact on the fact that it's still that ratio. It has no impact. So when you get this final answer, this answer has no idea that you came from degrees or radians. So the answer is always in radians. You're just going to have to remember that. So what I need to put here is something like rads or radians per hour. All right, it's 2:20. We've done 2 problems. Street light, and then we have the conical cup. Pardon? It's a water. What? It's a beer bong? That's what everyone seems to associate with that better. I don't know why. So what do you want to do? I'm going to give you the choice here. The street light is a situation where you have a lamp, a street light, and you've got this person who's running away from the street light, and then his shadow is in front of him, and you're trying to figure out how fast the shadow is moving away from him. Or the one with the conical situation where you have water being poured into a cone, a conical cup, and it's coming up initially very fast and then it starts to slow down. You want to do that one? What's that? Yeah, this one's probably going to be more useful to you. I'll reverse it. Yeah, I'll reverse it just because. There we go. So that's the one where I reversed it. Okay? So we're going to change the problem slightly. We're going to say a conical cup is 4 inches tall and 6 inches wide. Whatever fluid you want is not being poured out, is being Well, they don't want to fill it up. They want to take it out. Wow. All right, so is being removed. So water is being removed from this at a constant rate of 2 pi cubic inches per second. How fast is the water level rising or falling when the water is 1 inch from the top? All right, let me just start with some pictures. Hope I have time to finish this one. All right, I have a cone, right? Is the cone changing? No, cone doesn't change. This thing is 4 inches tall and 6 inches wide, I think. Yeah. Okay? That's not changing. In the general picture or in the instant in time, the cone is the same. You can't see that 4, can you? 4. What is changing, though? The level of the fluid, right? The water level, the beer level. The beer level, okay. Sounds like you are convinced that it needs to be beer. So, with that in mind, let me see if I can get a... Are we going to do an amber? Are we going to do Guinness? You want to go with Guinness? Just kidding. I don't know what kind of beer that is. Yeah, I can't... Is that... we'll just go with that. It's probably not going to come out very good, but... Okay, this is our beer level in here, right? That came out okay. That's changing, right? That's actually going down there, yeah. Are we going to put the little froth on there? All right, so this is actually coming down, right? The water level is coming down, or beer level, whatever. All right, man, what do we know? I mean, let's start maybe what we're given, what we want. I haven't even labeled any variables. I don't know. Let's draw that instant in time, though. It's going to be too hard to go back and forth between those colors. Your beer just turned nasty blue. Okay, at the instant in time, do we have anything? How fast is the water level? We're saying dropping, not rising. When is 1 inch from the top of the cup? 1 inch from the top of the cup. Crap, I need to bring that back up here then, like this. 1 inch from the top. Do y'all agree with my pictures so far? The instant time is on the right. The general picture is over here. So in my general picture, I should probably label some stuff because it's changing, right? But maybe what we're given and what we want will help us. What are we given? The rate at what? Water is being chugged, beer is being chugged out of a cone at a constant rate, that's a derivative, of 2 pi cubic inches is a measurement of what? Volume, right? This is a volume. It's being chugged out at 2 pi cubic inches per second. So I'm being given an instantaneous rate of change in volume. Am I? Right? Am I not? So I'm going to call what I'm given dV for volume, dV dt. And it is coming out, so negative 2 pi. Does everyone agree with my interpretation of that word problem? The change in volume for this beer chugger is exactly negative 2 pi cubic inches per second. Is that fast? Yeah, I think that's fast. Yeah. Because 1 cubic inch, right? What's 2 pi? 2 pi is about 6. So like 6 cubic inches. Just imagine 6 by 6 by 6 cube every second. I don't know, maybe some of you, that's like, nothing. Who knows? All right, so that's our, what do we want? How fast is the water level falling, right? Falling for us when it's 1 inch from the top. So come back to your picture. R is then what? You want to call R? The rate that what falls, though? Okay, so we need the water level in our picture. Where do you want it to be labeled? Where's the water level? Isn't it where we're right here, like this edge right here, straight across? Isn't that how high it is, the water level? So what if I label it like this? From here to here, like that. And why don't I call it H for like the height of the beer or the height of the water? I could call it Y because it's like vertical line, so Y-axis type thing. I'm just call it H for height. If I draw it like that, I want to know how fast that's changing, right? At exactly that moment over there. So I want dH dt. When do I want it? 1 inch from the top. But I need that in terms of what I have over here. So 1 inch from the top really means that H would have to be what? 3, right? Because it's a 4-inch cup. If I'm 1 inch from the top, that means I'm 3 inches from the bottom. So I need to interpret that and say when H is 3. It's kind of a critical little point here. Y'all got it? Well, I actually have quite a bit of information here. Let's go back over here. I'll label this over here. That's 3. We know that at the instant in time. And I only have 12 minutes, so we've got to pick up the pace here. I don't think there's any other information that is out there. I think I have what's given to me, what I want. I have when I want it. I've got my pictures. So what's the only thing really left to do? Find the equation. I need to relate the height of that conical thing to the volume. What's the volume of a cone? Right, because that's a cone, isn't it? So now you got to break open your books or Google volume of right cylindrical cone or whatever it is, and you find that the volume of a cone is, so I'll go to a new page. If you go and you look it up, it'll probably have a picture like this. It'll say if this is your height, it'll say if this is your radius, then the volume will be 1/3 pi r squared h. That's what the volume of a right cylindrical cone is. That's what it is. So, back to this. If I write that down, which I'm going to, volume is 1/3 pi r squared h. Well, that's my question now, because this volume formula, right, we are not interested in the volume of the cup, are we? We're interested in the volume of our beer, right? How much is left? All the cup does is keeps our beer in a certain shape as it's getting chugged away, right? So this volume formula applies to the beer, not to the cup. So do you know something about the height of that beer? Yes, and in fact, if I differentiated this, a dH dt would pop out and I'd be happy about that, wouldn't I? And on the left side, the volume, well, I'm going to differentiate that and I'm going to get a dV dt, which I'm happy about also. What I'm not happy about is what? The R, because I don't know anything about R over here. So like in the last problem, let's try and not have the R there. And this is where things get tricky, and I need to show you because we have 10 minutes and someone's got to show you this for the first time. So here's what I want you to see, is that as this height drops, the radius changes, doesn't it? The lower I go on the height, the smaller the radius becomes. The bigger the height is, the larger the radius. But it's always keeping some constant proportion because of the cone, right? On the outside, the cup itself. So what I want you to do is imagine coming in here with a sword or some sort of cutting device, and I want you to cut that cone right down the middle, right? I want you to peel the front up. Now, let's act like the beer's not in there, okay? It is, but it's frozen, all right? You cut it, and you peel off the front. You look at a cross-section of this. That's what I'm about to do over here. So I realize I've run into some problems. I have some major issues with that R squared right there, and I need to resolve that issue. So I go to a new page. I cut this cone. Oh, your beer's on the ground. But you're going to solve the problem, and that makes you happy. Now you have a new problem, right? You're all out of natural light. I'm just kidding. Is that a picture of the level of the fluid in the cone? All right, we said that, it was 4 and 6. It was 4 high, right, and 6 wide. So what if because I kind of see this, I don't know if you see this, if I cut that right down the middle like that, I actually can create 2 right triangles. Do you see those 2 right triangles? So it looks more like this. We have big triangle. We have small triangle. I'm just going to write them side by side. They both have this angle is the same, the 90. They both have this angle is the same. Do you agree with that? And that means that this angle obviously has to be the same. So these are what we call similar triangles. And the property of similar triangles is that if all the angles are similar or equal, then the ratio of the sides are equal. The ratio of the sides must be equal also. So give me the dimensions of the big one here. This big triangle, what are its dimensions? The height is 4. The width up there, it was 6 the whole way across. So we cut it in half, so it's 3, right? Okay, this right here on my small one was the height of the fluid, right, which we called H. Not fixing anything in time yet. And this side over here was R, and we don't know what that is, do we? Okay with that? But because of similar triangles, I can now set up a ratio. What I know is that, and I can do this different ways, I could say 3 divided by 4 must be equal to this ratio, R divided by H. You're fixing it in time, though. We can't fix it yet. Because remember, we're trying to figure out what's happening in that with that radius in our formula before we fix it, so we can differentiate it. What we're going to wind up doing here is, maybe you can see this, is do you agree that with this equation, I can solve this for R? Couldn't I solve that for R? Just multiply both sides by H? And you would get that R must be 3/4 H, right? So as this fluid comes down, right, your radius is always 3/4 the height, always. No matter where you are on in this cone, your radius will always be 3/4 of the height. And that's very powerful because when we come back here, I'll just do it right here. We go back to where we were looking at this formula, volume equals 1/3 pi r squared h. But we just said that the radius was 3/4 the height. So I'm going to replace this r with 3/4 the height. So our new volume formula becomes 3/4 the height squared times the height. Do y'all see that? I replaced r with 3/4 the height, and then squared, and then the h. Now what does my formula have in it? What 2 variables? V and h, and that I'm happy about. But I have to clean it up a little bit. I actually need to square this. So when you square 3/4, you get 9/16, right? 9/16. And then you bring it out here with the 1/3, comes 3/16. Pi. Now, you also squared the h, didn't you? And then you had an h there already, so it becomes h cubed. This is the volume formula for this particular cone. I see people looking at this. Are y'all all right with this or not? What's wrong? You got to tell me. This right here, square it, right? You get 9 over 16. But then you had 1/3 out front, so times 1/3. And I reduced that by a factor of 3. That 1/3 right there, this becomes 9. Well, you squared it. So you did 3/4 h times 3/4 h, and that gave you 9/16 h squared. It's no longer inside the parentheses because you squared it. Now what? I only have 4 minutes, 3 minutes. Find the derivative of that with respect to time. So what's the derivative of the left side? dv dt. It's still with respect to time. And then we had 3/16 pi, that's all a constant. Now the derivative of h cubed. 3/8 squared times dh dt. Do you know dv dt? Yes, that's 2 pi, isn't it? Or negative 2 pi. Do you know what h is in this particular problem now that you can fix things in time? Yes, it was 3, wasn't it? Do you know dh dt? No, but that's what we want, right? The rate at which the height is changing. So plug and chug. Negative 2 pi. Oh, that was no pun intended, but that was pretty good. That's good. I like that. I really like that. All right. What was h? 3, right? 3. So 3 squared. Plug and chug. That's great. Any questions on where I got any of this? dv dt is given. Here's our moment in time. H is 3. Plug it all in. So let's see. 3 squared is 9. And then, hey, this 3 and this 3 is 9. So that's 81 over 16. Pi. And then dh dt. And then I can divide both sides by pi, and it's gone. And then multiply by the reciprocal. I'm getting something like negative 32 over 18, or 81, equals dh dt. What is that as a decimal? 0.395, yep. Negative 0.395 is dh dt. Yeah, what are my units? What is it? Inches? What was the height measured in here? Inches, right? Okay, yeah. Inches per, and then time was measured in seconds. So right at that instant, right at that instant, that the water level is 1 inch from the top as it's coming down, right as it's 1 inch from top, at that instant, the rate at which it's coming down is about a third, about a fourth of an inch a second is how fast it's coming down. Whew, 240 exactly. So out of your homework for this section, I think that's probably it. I think we've done enough related rate problems. What I'd like to do is maybe send a take-home quiz with you maybe next time and give you maybe a couple of, like a week or two to work on it, you know, just kind of knock out a few problems at a time, because these take time to set up and get confident with it. No, next class I'll hand them to you. But let me give you something that you can work on. This is what? No, this is. I'm just going to give you some homework problems, then I'll give you a take-home quiz later. All right. So out of page 132, number 5 is very similar to what we just did. 11, 13, where's the rocket? Hold on. Where's the rocket? Oh, there we go. 37. Let's start with that. These problems get pretty elaborate, as you might imagine, but those 4 are very similar to what we've done so far. 37 is a little different, but I think you could probably figure it out. Have a good day.